Hello and welcome to this video about matrix proofs. In this video we'll prove these remaining transpose proofs. We've already proven some other theorems about transposes of matrices in other videos in this playlist. The last of these proofs states that when a matrix is multiplied by its own transpose, then it's symmetric, that is, that it's equal to its own transpose. So now to prove the first statement in this list, we'll set A and B to be equal to these expressions in ijth entry notation. We'll start with the left-hand side of this proof. We'll expand it out into ijth entry notation. We can bring these terms into the same pair of square brackets, because they are added first and then transposed second. Then we can bring the expressions for these matrices into the same pair of indices, by enclosing them in round brackets and placing the indices outside these brackets. Then we can transpose this by switching the ij pair around. We can then separate these expressions for the entries of the different matrices by removing the brackets and giving them separate indices. Then we can separate these expressions into separate square brackets, making them into separate matrices. We can then untranspose them and put the transpose indice on top. We have to swap these indices again to do this. And then we can finally rewrite the matrices using their variable names, thereby completing the proof of part A. Now to prove part B of this proof, involving this multiplication by a constant. We'll start with the left-hand side and expand it out into ijth entry notation. We can then bring the constant k inside the square brackets. Then we can transpose this matrix by swapping the ij subscripts around. We can then bring the constant k outside of the brackets. Then we can rewrite this matrix as a transposed matrix while swapping the indices. And then finally we can write this matrix out using its variable name, thereby completing part B of the theorem. Now to prove this statement, which says that transposing a matrix twice brings it back to its original value. This is fairly obvious because it swaps all of the entries back to how they were. So we'll prove it using this ij notation. We'll expand it out into ijth notation. Applying the transpose swaps the ij indices the first time. And then applying the transpose function again swaps the ij indices back to where they were. And rewriting it using the matrix variable name will give us back the original matrix before we transposed it twice, thereby completing this part of the theorem. Now to prove part D, which doesn't look obvious, but can be proven simply. The functions inverse and transpose can be swapped in order, but still give the same answer. So we'll prove this by showing that the second term is both a left and right inverse of A transpose. You have to look carefully at it to see it. I've written the different matrix variables with different colours so as to better track how they get manipulated by past theorems. So we'll multiply this term on the left of a transpose and swap it and place it inside these brackets and then transpose it using a past theorem. This inverse pair will multiply together to give the identity matrix because one of them is the inverse of the other. And the transpose of the identity matrix is obviously the identity matrix. It might be a good idea to try to prove it. A quick way to prove it is to remember that the identity matrix contains nothing but zeros in the non-diagonal region. So if these entries are swapped, they'll remain zero and won't get changed. So we'll multiply this term on the right to show that it's a right inverse. We can swap them like this using a past theorem. Then the matrix A and the inverse of A multiply together to give the identity matrix like before. And the transpose of the identity matrix is obviously the identity matrix, so we've shown that this term is both a left and right inverse of A transpose. So we've proven part D. Now to prove part E, that this statement is true. I've used different colours for the matrices to keep track of them as we manipulate them. This particular matrix is symmetric because it's equal to its own transpose. So we'll manipulate it according to a past theorem. Then this matrix has been transposed twice, which brings it back into its untransposed original state, thereby completing the whole proof. So I hope that you found this video to be helpful and educational. and maybe even interesting. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video, and thanks a lot for watching.